I am back, and it's taken me a little while to, like if you saw the first lecture, you know that I'm not able to use my iPad to write notes, so I've had to PowerPoint the stuff up for you. Again, my offer is good on this. If you'd really like to see me write stuff out, I can. I'm just having to get through the best I can while I'm at this conference. It's lunch, so I'm taking the time to record this now. But yeah, for some reason students seem to like the handwritten notes better, but I'm just having to do what I can do. The handwritten part isn't going to work with the internet here. So what I'd like to touch on today is continue this conversation. The first lecture I showed you was on mathematical induction and basic mathematical induction, the straightforward principle of mathematical induction. But in certain cases, we need a stronger form of that. We can't always just refer to the one thing previous and use that to prove the induction step of mathematical induction. Sometimes we need to assume all of it. Now, what I want to show you is that that's okay, and really want to show you a variation of that that's probably more useful to us. So let's get started with what we call strong induction. Okay, it's still induction, but this is like the stronger form of it. The idea is this. Suppose we want to prove a statement P that's dependent upon n for all integer n bigger than or equal to a. So we've got some kind of starting point. And again, I'm cautioning you on this. If we're trying to prove something for all real numbers n, we cannot use induction. That's not an inductive proof. That needs to be something else. Okay, but if we've got some kind of statement we're proving for integer n, and we've got a starting point a, then just like before with induction, we prove that initial statement is true. I don't know if you can see this or not. I'll put it up here. Show that initial statement is true. And then we pick some k out here and assume, this time the difference is we typically assume k is true and we show the next one. That's regular induction. What we do here is we assume everything from k back is true and show that k plus 1 is true. Okay. Now again, I want to caution you that I think the part of induction that gives people the EBGBs is that the fact it seems like you're assuming the theorem is true and then proving it's true, and you can't do that, and you're not doing that. Okay, let me illustrate. I'll do this a little better. You know, we've got these conditions. Think of it kind of here they are. These different statements we want to prove true. We're proving the initial one. Okay, that's what we talked about, and then we're assuming. Now, see, this is where you're not assuming the thing is true. You're assuming that it holds from the initial point up to where you are. This piece of k statement. If we assume that, it proves the next one, the statement for k plus 1. That's what we have to show. Now, we have not assumed that the theorem is true in doing that. Okay, we've just said, well, if it holds up to k, then it would force k plus 1. But when you have both of those statements, okay, this is important. When you have both of those statements, then you can look back and say, well, a plus 1, well, you know, the statement for a is true. That means a plus 1 is true. Oh, and these two are true. That means this is true. And so on and so on. So it's an okay thing to do. You know, you got to get your head around it, okay? But the important thing is that we really aren't assuming the theorem is true and then using that to prove the theorem is true. Okay, and I'll show you kind of how this is useful to you. Now, this is the general statement of it. I'll be honest, the homework I'm going to give you will use a variation of this, but I want to show you this so that you understand the variation. Okay, so I'll show you an example, and I'll just, you know, not because we're going to have a homework problem like this, but just to show you how strong it is. It's a really neat form of induction. So here's a classic theorem from your past, the fundamental theorem of arithmetic, which says that every integer 2 and bigger has a unique prime factorization, which you know to be true. You've believed that probably since you were in grade school and you were finding least common denominators of fractions, right? So one of the things that we always did back then is we do factor trees where you take a composite number and you break it down into its factors. And so you had so many factors of 2 and 3 and 5 and 7 and so forth, right? And you learned how to find the least common multiple and the greatest common divisor using those prime factorizations. Okay, that's a little blast from your past. I don't know if anybody's ever proven it to you. So let me show you how you prove this. We have a starting point 2. It's 2 is a prime, and it is its own unique prime factorization. Okay. Now this is where it becomes important that we have this strong induction. If I jump out here to a larger integer, say 6 for example, okay, using the standard induction, I would look back at 5 and say, okay, 5 has a unique prime factorization. The problem is that factorization has nothing to do with 6, right? 6 does not have a prime factor of 5 in it. However, it does have 2 and 3. So we need to be able to reach all the way back. In fact, if I did something like 242, it'd be important that I can reach back and get that 2 prime factor. Okay, so we make that assumption. Now suppose you've got that this holds for 2 on up to k. Okay, now it's a suppose. It's not. We're not saying. We're not saying suppose the theorem's true, then it's true. That's not what we're saying. We're saying, okay, suppose it holds up to here, okay, up to k. And now let's take a look at k plus 1. Well, k plus 1 is either going to be prime or composite. If it's prime, it's its own prime factorization. Done. Okay, so that case is done. If it's composite, then it's got to have factors that are smaller than k plus 1. And it may have several prime factors. So you take the smallest one. Let's call it a. And then a times something will give you k plus 1. So we'll call that other something b. Okay. Each of those, by our assumption, has a unique prime factorization because it's a number less than k plus 1. Okay, bigger than 2. Bigger than or equal to 2. So since each of those numbers has its own unique prime factorization, the product of the two will be unique. And that's it. So k plus 1 then has a unique prime factorization. We're not done. Therefore, right, the therefore is very important because that actually is what proves the theorem, right? It's like, oh, well, now that you got that, you can go back and once you got 2, you got 3. Once you got 2 and 3, you got 4. Once you got 2, 3, and 4, you got 5, and so on. Okay? So, there we go. A classic theorem from your past actually proven using strong induction. Now, the proofs that I assign you, the problems I assign you, won't be that tough. We're going to go back and do something that seems a little simpler, but you have to kind of understand where it comes from. We really are using the same theorem. We're just using a variation of it, okay, where we know exactly how far I have to reach back. With the theorem I just showed you, we had to sometimes reach all the way back. In a case where it's kind of fixed how much we have to reach back, then we use this variation of strong induction. It's an equivalent form of the same thing. It goes like this. Suppose that we want to prove it, the statement dependent upon n for integer n, and we've got a starting point a. Then what we do is, let's say we want to, we know how far we have to reach back, okay? So we prove enough things at the beginning to where when I get here, I can reach back and get those things, okay? So m is involved in what I call kind of a minimum reach back number. Okay, in a second I'll show you something. If you know Fibonacci numbers, you know that to get a Fibonacci number, you reach back to the two previous and you add them, right? So I have to reach back 2. We always reach back 1, I need to reach back one more. So M in that case would be 1. And I would prove the statement for the first one and the second one. And then your induction step is just like before, except that we make sure we start at that point and not back here. All right, so it's a little different, but it's logically just the same thing. And it really does work the same way. You just do a few of your initial steps as opposed to one, because like before, it didn't matter. There wasn't a fixed number I had to reach back. Now there is, and so you make sure you have that fixed number of things done initially, okay? And then once you make your induction assumption, all these things hold, then that forces the next one. Then you can go back. This really is a minimum reach back kind of thing, and saying, well, you can reach back as long as you've got at least 2 things, right? So once you have that step 2, that inductive step proven, then you can go back to P of A and P of A plus 1 and say, oh, well, that gives me 8 plus 2. And then you can look at those 2 and get the next one and get the next one and so on. So it really is equivalent. I'll give you an example of how this is useful. I'll give you a couple examples of how this is useful. One is what I kind of call the postage stamp problem. Prove that by using 11-cent and 4-cent stamps, we can build any postage amount 30 cents or greater. Okay, now this is the kind of thing you probably want to diddle with and again, when I show you proofs over Tegrity, I can't show you. I always try to do this when I work at the board. I'll go off to the side and I'll start scribbling. You do a little scribble work here, and you can kind of convince yourself that's true. The way to prove this is really we want to use induction, but we want to use the strong induction, the variation I'm showing you, because once we get things up to a certain point, as long as I can reach back, 3, I can always add a 4-cent stamp to it and get the next one, right? So 4 cent here is very important. We're going to have to show 30 cents. We can do it. Build it out of 11 and 4-cent stamps. 31 cents, 32 cents, and then 33 cents. So our M in this case is 3, 3 additional. Once I have 33, 34 is no big deal. Go back to 30 and add a 4-cent stamp. Right? 32, go back to 30. Wait, I didn't do that. 34. 35, go back to 31 and add a 4-cent stamp, and so on and so on. Okay? So this is the kind of thing that you probably need to just kind of diddle around and figure out on scratch paper. But if you do that, you'll notice that, okay, at 30 cents of postage, I could do that with 2 11-cent stamps, that's 22 cents, and then 2 4-cent stamps, that's 30 cents, right? 31, you end up, I think you can do that with like 1 11-cent stamp. That would give you 20 cents left, and then you can do that with 5 4-cent stamps. 32 is easy, that's 8 4-cent stamps. And 33 is easy, that's 3 11-cent stamps. Okay? The rest of it then comes from this inductive step. This is all our basic step, right? We're proving the single cases at the beginning. And now we say, okay, suppose we can build any amount from 30 cents to K cents where K has to be at least 33, okay? Because I have to be able to reach back, 3, really, K plus 1, reach back 4, but 3 behind the K, right? And consider K plus 1 cents of postage. Well, the way we say this, and it's pretty obvious at this stage, right? You say, well, since, by assumption, we know how to build K plus 1 and then minus 4, K minus 3 cents of postage, okay? And K minus 3 is very minimum, would be 30, right, cents of postage, which we've covered. We can build K plus 1 cents simply by adding a 4-cent stamp. Therefore, by strong induction, the statement is proved. Okay, so you'll have a homework problem or two like that. You'll also have a homework problem kind of like this. And these are Fibonacci numbers. I'm not going to get too deep into the Fibonacci thing right now, but the way you build them, you can think about the first one, the 0 term being 0. If you want to, you can leave that out. You can start at 1. But a lot of times they define it for, they start at 0. So f sub 1 is 1, and then the other ones, 2, 3, 4, you just add the previous 2. Okay, so f sub 2 would be 1. F sub 3 would be 1 plus 1, 2, and so on. So what we'd like to prove here is that f of 0 plus f2, adding just even term Fibonacci numbers, they add up to the next, wherever you stop with that even, the next odd Fibonacci number minus 1. Okay, there's all these cool things that happen with Fibonacci numbers. So let's prove this. Well, you'd have to prove that it holds, because we have to reach back to, our m is going to be 1. So we got to do the first one, which is 0, and we got to do 1. That way I can always reach back to, when I go to k plus 1, I can reach back to and get something that works. So let's take a look at n equals 0 case. That would be f of 0, which is 0. And if you look at the formula would be, we plug a 0 in here, we get f of 1, which is 1, minus 1 is 0. So it holds for that. Also note that for n equals 1, okay, that would be f of 0, and then if you put a 1 here, that's f of 2. So it's these first two terms. Then that would be f of 3 minus 1. Oh, well, first let's just add them up. That's 0, and then this one is 1, 0 plus 1. And so you get 1. And then if you plug this in the formula, that's f of 3, which is 1 plus 1. We just kind of said that. Minus 1. 2 minus 1 is 1. So the formula holds for the n equals 0 case and the n equals 1 case. Now we're ready for that inductive step where we say, okay, let's assume it holds for everything k up to k, all right, where k has to be at least 1, all right, and then I'm going to look at k plus 1. So we're assuming this formula holds for k. The only condition is that k has to be at least 1. Okay, that's the last case I proved it for in my basic step here. And then we say, all right, let's consider what happens at k plus 1. All right. So again, sums are pretty easy. We can always break out that last term. So we say, well, okay, we've got the sum up to k, which we have an assumption for k. We're assuming that this holds. And then we've got this other one. All right. So we use the formula for this. This is going to be f of 2k plus 1 minus 1. And then we've got this term. All right. So if you'll notice, though, right, this and this, okay, these are two consecutive Fibonacci's. When you add two consecutive Fibonacci's, you get the next one. So that gives us this and this give us 2k plus 3 minus 1. And that is really just this formula with k plus 1 substituted in there. So it holds. Therefore, and this is an important statement, therefore, because you've got the two basic starting points, and you've got the assumption now proven that, well, if it holds for some of these, then it, up to a point, then I get the next one. Therefore, by induction, it holds. Okay, it's just a little variation on what we did in the Part 1 lecture. Okay, but it's very strong. It now allows us to look back at more than just the previous one. If the formula involves things back a ways, or if the part of the definition requires that we look back at some previous things, we now have a way to do that using induction. Okay, all right. The assignment then that will deal with this, problems 12 through 14 in that same section, and we will tackle these. We've got to get we've got some set proofs, I think, left, And then we've got the induction proofs I gave you last time, and then with these. And I think that I'm probably going to stop here. Once we get these problems worked in class, we'll be ready for our first test. So the timing of that test is still a little bit in the air. Let's see how fast we move through things. I do want us to kind of, as we get better at things, we're going to start to move a little faster. But we'll start. I think probably on Tuesday. It shouldn't take us the whole time to get those set proofs. So we'll start doing inductive proofs on Tuesday. Maybe we can wrap them up on Thursday of next week, and then be ready. We'll talk about the timing of that first test. But this will be the last bit of material we put on the first test. Okay, so there you go. Enjoy. Have fun working those problems. Actually, I think once you get into it, you'll kind of enjoy these proofs. It's really a powerful tool, so I think you'll enjoy it. All right. See you back in Bowling Green on Tuesday.